Well, hello again. In this episode, we're going to discuss special relativity, which I talked about in the previous video as one of those mysterious components of the religion of scientism. So, this will be admittedly a critical review of this theory, which were here I put photos of three of the most prominent figures in the creation of this theory: Lorentz, Poincaré, and Einstein. Now, of course, I'm not the first person in history to criticize this. We have, for example, the great Nikola Tesla, who is said to have said something like, or described relativity theory as a beggar wrapped in purple whom ignorant people take for a king. So the purpose here is to lay out the arguments that convinced me personally that this isn't a correct theory, and not only that it's not really, of any depth. There's nothing particularly interesting in the end that comes out of it. Of course, if you're a zealous believer in scientism, this video will not be for you. But if you're sort of open-minded to the idea that this isn't a correct theory, here is my case for it. Now we have to do some background here and paint some background. Primarily, there are two concepts that I want to sort of let you sink in before we proceed. And one of them is Galilean relativity, and the other one is the Doppler effect. So we will spend a little bit of time discussing these. Now, before special relativity arrived, there was already a kind of classical relativity in the form of Galilean relativity. And here I read: Galilean invariance or Galilean relativity states that the laws of motion are the same in all inertial frames of reference. In particular, if you're traveling on a smooth sea, if you're below the deck, you would not be able to tell whether the ship is moving or if it's stationary. Inertial frame means that it's not accelerating. It's a steady state motion we're always speaking about. It's emphasized here, constant velocity. Now, what are the consequences of this? Well, we cannot speak about any absolute speed of an object. Moreover, inside an insulated inertial reference frame, no experiment can be conducted to demonstrate the relative velocity of the frame with respect to any other frame object. So these are the principles of Galilean relativity. Well, we can exemplify this, of course, when you're inside an airplane and it has reached its cruising altitude and it's a steady state motion, everything is nice. Well, if you shut the windows, you will not be able to tell that you're actually moving. There's no experiment, according to Galilean relativity, that you can perform inside here that would prove your constant motion or a constant velocity motion in relation to the ground. I mean, you can still drink your coffee, you can still play with your toys and everything like that. And we can even take the argument further that even if you're sitting down, in your chair at home, well, somebody might argue that you're not actually at rest. You're actually orbiting the sun at a speed of 67,000 miles per hour. So those are examples to illustrate this principle. Now we come to the question of the speed of propagating waves. Now it is generally acknowledged that you say that the speed of sound in air is 767 miles per hour, and the speed of light is, here it says 671 million miles per hour. But then again, you can ask the question, well, didn't you just say that you cannot speak of absolute speed? So what does this mean? It's sort of like saying that the speed of this woman is 66,000 miles per hour. Well, I mean, it could be any speed given whatever preferred reference frame you put out. But here we actually say something. So what does this mean? Well, in the case of sound waves, the speed is measured with respect to the medium where the sound wave travels. Could be air, could be water, metal, or some other material. Now, maybe I got these a little bit in the wrong order. Let's put it like this. So the problem here is that light was successfully modeled as an electromagnetic wave in the 19th century. I mean, here you see the Maxwell's equations that actually derive light as an electromagnetic wave with a particular speed, which we call c. And then the puzzle is, well, I mean, if we look at sound, well, it has its medium to travel. So if we think about light, well, the question is, well, what's the medium in which it travels? What's the medium? Before we move on, there's the other concept which is important here. So we have, on the one hand, Galilean relativity, and now the second important concept that should sink in is the Doppler effect. Now, what it says is that if we have a vehicle moving here, for example, in air, producing sound waves, well, in the direction of the velocity of the vehicle, the speed will contribute in such a way that the distance between the crests of the wave here are smaller than if it had just been stationary in the medium, because it's moving along. And shorter wavelength, that is higher frequency. And of course, the very opposite effect occurs in this direction. And here you have classical formulas how to calculate the frequency shift depending on certain velocity parameters that you plug in here. Now, so it was postulated that, well, the light travels in a medium that we call the ether, which I guess they assumed was fixed in space. But if this is the case, then we ought to be able to, if we have a light source traveling through this ether medium, then we ought to be able to detect some kind of Doppler effect here, to measure the ether wind, as they put it. And this is the Michelson-Morley experiment where they sort of attempted to show that, well, as we mentioned before, the Earth is, orbiting the sun at a considerable speed, and they assumed that, well, the relative speed at which our laboratory now is traveling with respect to the ether wind is at least that of that magnitude. And here you can see some kind of illustration of the experimental apparatus, but they didn't detect any Doppler shift. So it was a null result. Now here's where Lorentz comes in, and he tries to reconcile that. Well, let's assume that there still is some kind of ether, even though we can't detect it with this Doppler experiment. So in order to reconcile these notions, well, he needed to introduce some kind of length contraction or time dilation, so that, well, there is an ether, but we cannot detect it because when we're traveling through these phenomena occurs. So we will not go into particular detail of that. But there are some points I want to make about the assumption of an ether and why it's kind of dubious when you think about it. It's understandable that they were looking for a medium given that they had wave equations for light. But if you think about it carefully, if they had detected the ether, in my view, it would have violated Galilean relativity. Because if we move back to what we said here, inside an isolated inertial reference frame, no experiment can be conducted to demonstrate the relative velocity of the frame with respect to any other frame. And of course, a positive Michelson-Morley result would have provided this kind of experiment. I mean, let's suppose one laboratory measures their respective relative velocity to the ether, and then there's another laboratory somewhere else measuring their relative speed to the ether. Well, then they can later talk with each other and conclude that, well, our relative velocity was this and this. So I think that you would have to abandon Galilean relativity if this had been the case. The second argument why it's kind of dubious is that, well, electromagnetic waves are essentially a force field. I mean, the only thing you need to multiply the field with is some kind of charge, and then you get a force. So in the case of sound waves, you have forces in the medium displacing matter. I mean, molecules, atoms that are displaced and oscillating. But in the case of a hypothetical ether, well, you would have some kind of force displacing electromagnetic forces, essentially. The force displacing forces, and then what's that force? Where does that come from, and so on? You kind of run into some kind of infinite regress, you might argue. So now we come to special relativity, and I guess here it's what it says is that, well, even if we cannot detect the ether, let's just say that the speed of light is c. That's what it is. Of course, they inherit some principles of classical mechanics and Galilean mechanics, say that there is no privileged reference frame. I mean, there's no absolute space or anything like that. But then there are some various formulations. I can give you a number of them here. The speed of light in vacuum is the same for all observers, regardless of the motion of light, source, or observer. Light is always propagated in empty space with a definite velocity, which is independent of the station motion of the emitting body. Well, I guess this is the illustration of what it says. I mean, it's like, well, the speed of light is c in all directions. That's what it is in any reference frame. But here comes the crux, because we have an experiment or a technology which is called the Doppler radar. So here you see an example where a police car, which we can assume is at rest here, and then we have a moving vehicle, and it is bombarded with electromagnetic pulses here, which are then incoming and then reflected. But since the car here is moving in this direction, analogous to what I showed before, well, the crests will be returned at a frequency which is higher, because the wavelength, the interval between the crests here will diminish. We can see how this is described in Wikipedia. We have the Doppler radar, illustration of a military police using this. And they move on to say something quite interesting here. Is that there is no need to invoke Albert Einstein's theory of special relativity, because all observations are made in the same frame of reference. So that's kind of curious. The typical excuse you have for not invoking Albert Einstein's theory of relativity is because the velocity is assumed to be so small compared to the speed of light that the relativistic effects disappear. But here they say, well, it's because the observations are made in the same frame of reference. I haven't seen that before, and I don't quite know what it means. I don't know if anybody knows exactly what it means, but anyways, they present the ordinary classical formulas and arrive. It's only here that they do a slight approximations and assuming that this is negligible compared to C, and they arrive at this formula. But that isn't invoking any special relativity formula. But then again, the situation here is that in the inertial reference frame of this vehicle moving at constant velocity towards this police car, we must have a situation where the speed of these crests, this light wave, is higher than this. There is no way you can get this otherwise. You can see it explicitly in the formula. Here you assume a velocity of the incoming wave, which is blatantly larger than the speed of light, because you just add them together. So what did it say? Well, light is always propagated in empty space with a definite velocity, c. Well, I mean, if this experiment doesn't disprove that claim, well, what does special relativity really say? Does it say anything? If this isn't a disproof, well, what could be a disproof? Now, the technology here, I don't know if it came into use quite late compared to when the special relativity theory was initially formulated. So the observation that this is a blatant violation of the principle of relativity perhaps was too late for it to be argued because people were so dogmatic about this theory at the time. So perhaps it was just too late to make the claim. This, here I write, well, the Doppler radar experiment can only be explained if we assume that the speed of the incoming light wave is greater than the speed of the outgoing light wave in the inertial frame of the moving vehicle. And that has to be in violation of special relativity. Now, somebody might argue that, well, can we use some Lorentz transformation to explain this? Well, no. The velocity appears squared in the length contraction and time dilation formulas, so it knows of no direction. Any sign here, plus minus sign, just disappears. So whatever contraction that would affect this incoming wave, it would affect the outgoing wave in the same way. It doesn't know of any directionality. So these are the conclusions then classical physics and Galilean relativity hold, both in the case of the null result of the Michelson-Morley experiment and in the case of the Doppler radar. And there is no case for special relativity. But when we can move on to talk a little bit how this theory lives on. What started off as a kind of particular reasoning about the speed of light and so on, then becomes like an intrinsic property of space-time that affects every object. And here you can see, the typical kind of high school, first year university kind of exercises where students are asked to calculate some time dilation according to some observer, blah, blah. Here it says, for example, time slowed as seen from Earth. How can such an observation even be made? Somebody here observes that time slows down here. What does that mean even? Then I think in sort of the lack of actual experimental evidence for anything, you start with some kind of circular reasoning, which is almost like, special relativity tells us things about the speed of light. Therefore, any experiment that has to do with the speed of light proves special relativity. And I guess GPS is an example. When the actual engineers behind the GPS systems are asked, as far as I've been told, they say that, well, no, we're not using any special relativity, as could be expected, because, it's explicit here. The engineers behind the Doppler radar says explicitly, we do not use Einstein's theory of special relativity. Then we have also what I could describe as anecdotal evidence. We have the phenomena of particles entering the atmosphere of the Earth, and it is somehow observed that their decay rate is slower. It has a longer lifetime for some reason. And then, they think that, now we can use this observation to prove the time dilation of the special relativity theory. So that because the speed of these particles is so great, there's a significant slowing down of time in these systems so that their decay rate goes down. Now, the problem here is well, there is no privileged reference frame. The situations could be modeled such that it was the Earth that approached the muons instead of the other way around. Yeah, it's perfectly all right in both special relativity and classical physics to, instead of having this move at a significant speed in this direction, you could instead have the Earth moving like that. And then you would have the exact opposite situation. So again, it's relativity seems to be able to prove anything and nothing. Then we have also these, which I here put the title Esoteric proof. Well, then we have all these claims about relativity predicting antimatter and an electronic spin, and that's pretty much based on the Dirac version of quantum mechanics. But just to illustrate the level of arm waving, here we put some expression for the energy, which has some kind of invariance that is Lorentz invariant. So we're just basing it on some kind of formal mathematical, I mean, a common invariance of two mathematical objects. Then we replace this with an operator, differential operator, and then we want to take the square root of an operator, which is then done by some kind of Taylor expansion, formal Taylor expansion, and then you have further manipulations, and then in the end, in some mathematical system, you end up with something which could be interpreted as negative energy eigenvalues of an operator, and that is then interpreted as antimatter. So there are so many levels of arm waving here that it cannot be used as a clear evidence of anything. It's very loose. So, well, can I say what about general relativity? Well, general relativity is a generalization of special relativity to accelerated reference frames. So, if we've concluded now that special relativity doesn't hold, well then general relativity cannot really be the underlying theory of any actual phenomena. It is claimed to predict the bending of light in gravity fields. I don't know, haven't checked the accuracy of those experiments. Seems to me a little bit like anecdotal evidence again. But even if that's the case, well, general relativity is not likely to be the explanation. Well, what about this formula? Well, this appears already in classical electrodynamics. It has been attributed to special relativity in some kind of loose fashion again. What the formula actually means entails, I'm not the expert to say anything about that. Well, so I hope this was an interesting expose. Maybe I have convinced one or two listeners of my arguments refuting special relativity. And well, hope to see you again soon. So bye bye for now.